So our next speaker is Glennys Farrar, coming from NYU. Glennys had a long and storied career in particle physics and understanding the nature of dark matter. And so I think, again, some of Steve's great interests. And I think a lot of the excitement here is the intersection of dark matter and sort of quantum chromodynamics, understanding that, what are possibilities for dark matter. Can they be a little more exotic than some of the things we've considered previously? And of course, today we will be hearing about something different, but that I think shows Glennys's breadth. So please.
Thanks a lot. Well, it's so wonderful to be here. Thank you so much. It's my second visit to Austin and the University of Texas. The first time was shortly after Steve and Louise were recruited here. And Steve and I were working on a paper at the time about R parity. And they invited me and I gave a talk and so on. And they invited me to their house, and it was really so sweet. They were completely delighted about having bought a refrigerator. They had just been out shopping for refrigerators. They felt like they were newlyweds again. Anyway, it's a very vivid memory. Anyhow, before I continue with the talk, I just want to remark about Helen. A very formative experience on me was in the early 70s when I visited SLAC. And I remember there was a talk, I think it was T.D. Lee, and Helen questioned something he had said. And he kind of didn't immediately agree with her, but she really stood up to him. And that was just like a revelation of this, quiet young woman standing up. Anyway, so thank you, Helen, for that excellent example. Anyway, well, it was hard to choose what to talk about because I've been working on a variety of different things. But I thought this would be a change up for what people are, what's otherwise going to be talking. And I know Steve would have loved it. And I suspect that, and it's really quite a breakthrough. So. The speaker can't see the time. There's a clock there, but the lights are in your eyes. Okay. So I'm going to talk about ultra-high energy cosmic rays. Their origin has been really a mystery. To give you a little background, this is the spectrum, oh, thanks so much, of cosmic rays. And, oh, sure. I have a better slide. We'll skip over immediately to this. Is this pointer? Myself organized here. You think this is the pointer? Found it. Thanks a lot. So at low energies of, say, less than 10 GeV, they're mostly from the sun. At medium energies, going up to, say, 10 to, the units that people use for the ultra-high energy cosmic rays are ecta-electron volts. That's 10 to the 18th electron volts, 10 to the 9th GeV. And going up to around that value, maybe a tenth of an ectavolt, it's galactic. And there's discussions about how they're made. So the ones I want to focus on are the really high energy ones, and there's a number of different theories about how they could be made and variety of evidence that it's extragalactic, and I won't go into it for lack of time. I'm happy to fill you in later. Trivia, you can't resist. At 210, about roughly the highest energy cosmic rays that are known have a few hundred EeV. And in their nuclei, a single nucleus with that energy is like a pro golf ball, quite staggering amount of energy. This is my favorite, that the relativistic time dilation makes the neutron have a lifetime of over 1 million years. which may or may not be detectable. You could imagine some source that produces neutrons. It wouldn't be deflected by magnetic fields, and the cosmic rays would all come from, you would actually be able to see them. And then the flux of the highest energy ones is really, really small. When you restrict yourself to above 10 to the 20th, a few 10 to the, let's say 10 to the 20th EV or 100 hectovolt, then there's less than 1 per square kilometer per millennium. So you can imagine the detectors have to be huge. A bunch of particle physicists, including.
If you, I would, the energy golf ball would have hurt.
No, because, well, you'd have to be in outer space for that to happen, because when it hits the atmosphere, it starts to interact. So by the time, but I haven't thought about the question of if it just went through you. If you were outside, I suspect it would just drill a small hole. And it's probably so small that probably it would actually do nothing to significant, but we'll think about this over drinks. So there's sort of two reasons that at least I got interested in the general topic. One is that in the late 90s, there was 2 different observatories that claimed that the so-called Greisensatz and Kuzmin bound was violated. Possibly many of you know what that is, but basically it's an effect that if you get to a high enough energy, around 50 EeV, then the center of mass energy of a proton interacting with a CMB photon, of which there's a huge abundance, 400 per cubic centimeter, that center of mass energy sits on the delta resonance, and you can get an inelastic collision producing a pion and a nucleon. And so that causes the final nucleon to have less energy. So below that energy, the energy losses are relatively mild. As it propagates, a cosmic ray could scatter on a photon and make E plus E minus pairs or something and lose 1% of its energy or something. But above that energy, you get a very short energy loss length. And so that means that there would be a cutoff in the spectrum, because at higher energies, you only see the nearby 10, 20, 50 megaparsecs, and at really high, sorry, did I cite that backwards? For high energies, you're seeing the nearby universe only, whereas at low energies, you see the whole universe. And so therefore, the flux of particles of the is sort of essentially cut off. Later on, it turned out this was a sort of false alarm, because both experiments in a different way had miscalibrated their energy spectrum. But anyway, a lot of people got quite interested, wondering, well, could this be some new supersymmetric particle that was somehow produced in some system and then traveling unimpeded by this GZK? Whoops. Can I go back? By this, I can't go back. Now I'm going to make a mess.
Use the keypad.
Thank you. Anyway, so this was a false alarm. The other reason that they're so interesting is that the center of mass energy of the collisions, when they hit it, so they hit a nucleus in the atmosphere and it fragment. But the initial collision there has a center of mass energy of something like 50 to 500 TeV, so vastly bigger than the LHC or conceivable experiment. So that was also another interesting reason to be trying to think about the physics of these systems. I'm not going to talk about this, but very interestingly, since there's a bunch of particle physicists here, the cosmic ray air showers cannot be explained by particle physics models. I personally think it's not some deep new particle physics, although I spent a few years working on that. I think it's, I could also be happily tell you about it, but there's two problems, one known as the muon problem and one known as the X-mass problem. People cannot adjust the LHC tuned particle physics models in order to explain the air shower data. But I'm not going to talk about that. The talk today is about what's the origin of these things. So the way we know, the way we know what we do know about them is that so imagine, this is sort of schematic picture of cosmic ray hits the upper atmosphere. It produces possibly thousands of secondaries, primarily pions and kaons and anti-lambdas, anything you can think of. The pi zeros decay instantaneously, essentially, to 2 photons, which then scatter off nuclei and whatnot, and they create an electromagnetic shower. And so that produces most of the energy goes into that, and that produces a bright streak of light in the sky. Charged pions, for example, and other hadrons hit an air nucleus. They get produced, but they're so relativistic that they don't decay, and instead they just keep interacting with air nuclei and until they get to relatively low energies. And so there's something like 10 generations of collisions before stuff hits the ground. And in each successive generation, the incident particle has less energy, and gradually the pions that get produced have low enough energy that they can decay. So somewhere, let's say schematically, in this picture, the muons start to get produced. And then the picture, by the way, isn't to scale. It's much more collimated, but I thought it was a pretty picture. Anyway, the two techniques that are used for detecting these things and learning about them is to have a telescope that can see the event from the side and a huge array on the ground of detectors. Let's see, did I have a picture of it? Yes, if not. So I could just say the detectors on the ground can measure the Auger one, which is the biggest, can measure electrons and muons and get some information about, you can infer the basic, based on how many muons there are, sort of what was the initial composition of the cosmic rays. Just a little history, Hess found cosmic rays. You hopefully know that story. It's very charming. I think he must have been an adventurer and he wanted to have an excuse to go up in the balloon. But he was shortly after people had discovered radioactivity and had a Geiger counter and or electroscope. And so he was going up in the balloon measuring the flux, the cosmic ray abundance, and it kept getting lower and lower, as you expected, with some exponential fall off. But then instead of continuing, it started to get bigger and bigger. And so he discovered, for which he got a Nobel Prize, surprisingly. The next really high energy event was reported in PRL in the early 60s. It was led by John Lindsley, who had I think as far as I know, it was almost a home experiment in New Mexico. That's those people setting out to do their experiment. And they had a ground array and they detected this event. The next really big event was discovered in Utah by the Fly's Eye group in the early 90s. It's sometimes called the Oh My God event because it had 320 EeV according to their estimate. Now, more with modern knowledge about how the air fluorescence occurs, that number probably should be 250. This is a schematic picture of Auger. The largest detector now is in the Southern Hemisphere in Argentina, Auger collaboration, and it has 3,000 square kilometers covered with 1,700 of these water detectors that are very highly instrumented. And so when they get, so it's a sampling system set up. The shower hits and you sample it. But then this is a schematic picture of it with all the 3,000 detectors and 4 telescopes, each, I mean, 4 telescope stations, each with a number of telescopes. And together they look out over the array. And so if it's a dark moonless night, which is about 10% of the time, then the cosmic ray shower, this fluorescence light that the electrons are making, produces literally light that can be measured by a telescope. And that's the calibration system. Yeah.
A historical point. Jack Koifel in Utah was doing cosmic ray physics in the 60s, in the mid 60s.
Yeah,
and
absolutely.
actually his neutrino scattering was one of the things that BJ was looking at, Bjorkane. Before there was deep inelastic scattering data from SLAC that led to Bjorkane scaling.
Yeah, yeah,
So-
that's a nice historical note to put. There's innumerable particle physics early discoveries that came from cosmic rays, like muons and pions and so on, before there were early accelerators. Okay, so this is the meat of the talk. I'll very briefly summarize the observational status. By now, the data's gotten really very good. It turns out there's really no GZK violation. There's an attenuation, a mild attenuation at the very highest energies due to this phenomenon, totally consistent with what you would expect. A very big problem, which is really the impetus for the research that I'm going to tell you about, is that all of the usual suspects that have been proposed up to now for what the sources could be have real problems. There's none of, until this suggestion I'm going to tell you about today came about, none of them could explain all of the things we know. But the kind of systems people thought of were AGNs, where the jets of an AGN would be very powerful, or, I mean, the energies are so tremendous, you sort of just imagine it has to be an extremely energetic system. Another one was suggested to be the collapse of a massive star producing a gamma ray burst, tidal disruption events, and so on. So what I want to, in fact, claim, I think is so strong, the evidence is so strong, I actually think this is the correct explanation. It's not many times in one's life you're in a position to say something like that with confidence. I'll explain to you why I believe that's the case. Interestingly, the crucial key to this is something that's seen in the data that has kind of been, people who've been thinking about it have had in the back of their mind, but its relevance was sort of underlined by a recent paper. But it's such a striking characteristic of the data that I think almost all of the cosmic rays, ultra-high energy cosmic rays, have to come from this single mechanism of the binary neutron star merger. And there's a ancillary prediction that because our process elements, that's heavy elements like, I'll talk about this toward the end, like xenon and gold and all those things, are produced in binary neutron star mergers. Since that stuff is around, that provides a natural explanation for these very high energy events like the oh my God event, which otherwise have been completely inexplicable. Okay, so see how I'm doing. So measuring the, this is a plot as a function of the log of the energy from can I see this? 10 to the 18th, so that's an electron volts. Below that, it's a lot of contribution from the galactic cosmic rays, so we're not going to pay attention to that lower energy region where it's more muddled. But at high energies, this is a picture of the spectrum. It's multiplied by E cubed, so it's actually a steeply falling spectrum. And the thing to notice, and what's this colored lines are showing, is the composition of the cosmic rays that are contributing. And that's determined by, well, this is the data. I won't try to explain to you how that's measured. The crucial thing is that at any given energy, there's not a wide range of compositions. What happens is, I have to say a parenthesis. The relevant parameter for acceleration of a cosmic ray, these are ultra relativistic, is what's called rigidity by particle physicists. It's the energy divided by the charge. And that's relevant because that's what governs the Larmor radius. And the only thing that the physical mechanisms that can accelerate it knows about, all of the models, all of the mechanisms that have been suggested are basically, starting even with Fermi's to discuss the first cosmic rays, are based on magnetic confinement. And so if something is going on, the charged particles are bouncing around between turbulent regions or crossing shocks or something. And but once their Larmor radius gets so big that it's sort of larger than the scale of the system, then they just escape. And so the cutoff of the spectrum for all of the different elements will be the same if it's expressed in rigidity. That's what you would expect in terms of your theoretical understanding, that leaving the accelerator, all that matters really is what the rigidity is. And indeed, that shows up in the data in a plot that's impossible to see. But this is from the analyzing the data for rigidity. So it's been established that rigidity is pretty much conserved at all different energies, the rigidity spectrum. And now here's this shocking result that nobody expected. It's a very narrow rigidity range. The rigidity range of all the cosmic rays is of the extragalactic ones is a factor of 2 or 3 in width. The central value is around 4 ectovolts. The high energy ones that are 100 ectovolts have a charge of 25, could be iron. The low energy ones have a low charge. And that's now quite well established. Now, why is it puzzling that the rigidity range is so small? The reason it's surprising is that imagine you have some accelerator that will accelerate to a certain rigidity, the highest ones that you've ever observed. Won't there be many more that can accelerate to a lower rigidity? This was quantitatively developed in this paper by Ehlert, Okonomou, and Unger last year, where they examined and there's a relation between the maximum rigidity and the luminosity of a source. I won't go into that. And so given that all of the suggested candidates for the sources have a broad spectrum of their maximum luminosity, that suggests that there should be a broad spectrum in even a power law spectrum in the rigidities. There's some maximum from the highest energy rigidity capable source, and then some much larger abundance of the lower rigidity capable sources. Does that make sense? That's what you'd expect. However, it's absolutely not like that. There's just a narrow rigidity range. So anyway, that was what was worrying me. And when I came up with this idea of the binary neutron star mergers, I won't go into it much, but there's also constraints on sources coming from this is a plot of the arrival directions from Auger, and this is where Auger is not sensitive. Telescope array is sensitive in that area and just sort of fills it out. And what you find when you analyze it is it's a very large dipole of order 10%, and no other multiples. And what that tells you is that the sources have to be reasonably abundant, because otherwise you'd have little individual hot spots, and those aren't seen. The last sort of piece of information that one has to take into account is at least some of the sources, at least the highest energy events, were produced by transients. And that you can figure out as follows. In general, cosmic rays are much harder to think about than things like neutrinos or high energy photons, because they bend in magnetic fields. And the magnetic field of the galaxy is a few microgauss, but it extends quite a distance in some directions, several kiloparsecs or even 10. And so given that they're nuclei with high charges and the rigidities are around 4 hectovolts, then they actually have quite significant deflections. And if you deflect, but miraculously, if you backtrack the oh my God event and a recent one that Telescope Array just a year ago discovered, they called it Amaterasu for the Japanese sun god, its energy is not quite as high. It's something like 220 EeV, so it's really up there. If you backtrack both of them, the region of the sky that they came from has nothing remarkable. There's a region called the local void, and there's no AGN, powerful AGNs in that direction. There's no starburst galaxies, which have an enhanced abundance of these long gamma ray bursts. That was one of the suggestions. So it really tells you that whatever is producing them is a transient. I was delighted about that because I suggested quite a long time ago that maybe tidal disruption events existed. This is before they had been discovered, and that they were showed that they could be possibly the source of ultra-high cosmic rays. And so I was thrilled that this work showed that some transient has to do it. But the tidal disruption events absolutely cannot. Tidal disruption events is when a star comes close to a central massive black hole of some galaxy and gets shredded, and then it's like it makes a temporary AGN. Not all of them do this, but some of them can make jets. So that was the thought I had had. And with a student, we studied SDS data and showed that there were 2 of those. Actually, Martin Rees proposed them, but they had not been discovered at that point. Anyway, so my heart was with tidal disruption events as the source, but they will fail the test of this narrow rigidity range. Okay, so these are the key conditions on the ultra-high cosmic ray sources. It has to have a big enough product of its the maximum rigidity that you can produce has is the product of the field in Gauss times the size in kilometers times the small number in front. It turns out that it's not hard to satisfy that. That just says that, oh, thank you, that this issue I was saying that you can only accelerate something as long as you can confine it. Many sources satisfy that. You have to satisfy the energy injection rate and so on. These are the 2 key new conditions, that this universal maximum rigidity and the anomalously high energy of these 2 particles. And so the suggestion is that it's they're created in binary neutron star mergers. And the motivation is just that binary neutron star mergers are really all the same, because the masses of binary neutron stars are within 5% of each other. And all of the observed binary neutron star systems have masses within 5% of each other. And the magnetic fields are produced by a gravitationally driven dynamo. So you can imagine that the magnetic environment is very, has what it needs. And it satisfies the other conditions. So I want to tell you in the last 5 minutes about the R process elements, which I think perhaps a lot of people don't know about, and it's really wonderful. This periodic table has been colored, so you know that hydrogen and helium were produced in the Big Bang. Other elements, the ones shown in green, are dying low mass stars. The supernovae, the exploding massive stars, are in gold colored. There's a few elements like beryllium are produced by spallation from heavier elements by cosmic rays. What else is there in this table? Well, anyway, you get down to the purple ones. And the purple ones are these so-called R process elements, which had long been understood couldn't be produced in the stars. And this is showing the abundance of different elements as a function of their mass. And the ones in red are the ones that are the so-called R process elements. So the term R process stands for rapid process. And it was coined by a wonderful paper called B squared FH by Burbidge, Fowler, and Hoyle in 57. And what they pointed out is that these nuclei had so many extra neutrons that in order to make them, you had to make them extremely fast, because otherwise the neutrons would decay. Because if they were in the intermediate process, it's not a stable configuration yet, but you kind of keep adding things, and those would decay away if you didn't add them really quick. And so they said they needed to be between 10 and 100 seconds. So this is a picture. I wish I had a movie of it, but I don't. This is a picture of the charge versus the neutron number for the different existing elements is red. The black is the ones that are stable. And the gray line here, I'm really sorry to people over there. I wish I had a pointer that showed both. The gray line here, so in order to synthesize something heavy, you have to add neutrons and protons, but because, and as you notice, it's kind of diagonal up till you get to around iron, and then it becomes neutron rich, and there's more neutrons than protons. But anyway, the way the synthesis works is to follow the gray line, and then by adding more and more neutrons, and then they have to decay into the stable nuclei. Anyhow, I just want to, I'll I guess, end with this. The theory, people had speculated for at least 20 years, maybe longer, that binary neutron star mergers might be the source of R process elements. The reason being that when you have two neutron stars, you have an abundance of neutrons. Now I think it's really very, very much, okay, can you guys see that? Oh, I should have been using this, I'm sorry. Anyway, this is a simulation, and the picture is that the binary neutron, the R process elements get produced, especially in a sort of equatorial toroidal, a sort of a torus. The reason it's very interesting why they're not in the central jet region is there's too many neutrons. There's so many neutrons in this ejection of all of the weak interactions that are happening. I think Steve would really love all of this. That they just destroy the, you sort of disrupts the process. In any event, this picture then I believe is a very compelling explanation for the ultra-high-energy cosmic rays because A, it explains why the rigidity spectrum can be so narrow, and B, the highest energy events are naturally explained as being part of these R process peaks. So I think that's where I'll stop. Oh, that's just a. Oh, well, I forgot. It's testable because it predicts that when there's when you get an I'm sorry. Is it okay? Okay. When you this production of ultra energy cosmic rays, as they leave the environment of their accelerator, they go through they're sort of confined for a certain amount of time because there's some magnetic field around, but without even being specific about the that process of escape, you can infer some very general predictions. And one is that they will be accompanied, every ultra-energy cosmic ray will be accompanied by some number of around 20 PeV neutrinos, only 2 of which have been discovered so far. But conversely, if you get a 20 PeV neutrino, it came from an ultra-energy cosmic ray interaction. Therefore, if this theory is right, if you see a 20 PeV neutrino, there will have been a gravitational wave burst, the one that was associated with the binary neutron star merger. And therefore, a prediction that can be tested with Cosmic Explorer and next generation IceCube is that there will be this correlation. Okay, now I'll stop.
Wonderful, thanks. I think Steve really would have appreciated a new theory and a testable prediction. Yeah, Katie?
Well, I was about to ask about IceCube PeV neutrinos, but I guess you've already talked about that. The other historical comment I wanted to make.
But let me just say, most of their neutrinos are produced by other processes. They're considerably low, it's like a factor of 10 or 20 lower in energy. There's this sort of special peak, only 2 of which have been discovered so far.
Thank you.
Sorry.
I also want to make a historical remark, which is, as far as I know anyway, my PhD advisor, Dave Schramm, together with, it was Schramm and Latimer, who first proposed neutron star mergers as a way of making the heavier elements.
Oh, great to know. I wondered where was the origin of that. Lots of people claim they proposed it.
You know how I found out? Luis Alvarez Gomez came to me and he said, "What? You don't know this?" So
Thank you.
Netta?
There's the abundance of binary neutrons is highly uncertain, right? So what can we say about how the abundance fits with this picture?
The abundant, I think there's a slide, or maybe I excluded it, but the you can calculate the rate, and of course the amount of production, it depends on that. And the abundance will work fine. They're sufficiently abundant to do the job with, if there's more than about 100 per cubic gigaparsec per year. The numbers, the experimental range is from 10 to 1700. And so sort of in the lower portion of that range. But if it was much less than 100 per cubic gigaparsec per year, then it might start to be a problem. It depends a lot on the efficiency of an individual merger, but with a conservative estimate for that, it looks so. Basically, the short answer is that it looks quite good.
Well, I think that's a great place to leave it because we now have lunch. So let's thank all 3 speakers again.